To find the equation of the inverse of a one-to-one function, we're going to follow the following 4 steps. Step 1, if necessary, we will replace f of x with y. Then we're going to switch the x and the y. Because remember, we know that if we switch the domain and range of a function, that'll give us the corresponding domain and range of our inverse function. So switching the x and y is like switching your domain and range. Then we just need to solve that new equation for y, and finally replace the y with the function inverse notation, the f inverse of x. So let's jump to example 6. We're given a one-to-one function, f of x equals x cubed plus 1. We're asked to find its inverse and check our answer, and then graph the function in its inverse, as well as the line y equals x on these coordinate axes. So let's first find our inverse. So our first step, we're going to replace that f of x with the y. So we're going to write y equals x cubed plus 1. Then we have to switch our domain and range. So we're going to switch our x and y values. That will give us x equals y cubed plus 1. Then we need to solve for y. So we're going to subtract the 1 from both sides. So that will give us x minus 1 equals y cubed. And then to remove the cubed, we need to take the cube root. So that will give us the cube root of x minus 1 equals y. And then finally, we want to replace that y with the f inverse notation. So we'll have the cube root of x minus 1 equals f inverse of x. So our inverse function, f inverse of x, is the cube root of x minus 1. Now we want to check our answer. Well, in order to check our answer, to verify that these are inverses, remember if we compose the functions with each other both ways, f with f inverse and f inverse with f, we must equal x, because that's another way of saying that the functions undo the work of each other. So in this case, you can kind of see it. If you have x cubed plus 1, you're cubing the x value and then adding 1 to it. Well, if we look at our inverse here, we're subtracting 1 and taking the cube root. So those certainly look like they would undo the work of each other. So let's verify that algebraically by composing the two functions. So I first want to find f of f inverse of x. So I'm going to find f of the cube root of x minus 1. So I'm going to replace the x value in my original function here with the cube root of x minus 1. So that will give me the cube root of x minus 1 cubed plus 1. So if we cube a cube root, we'll get the radicand, the expression under the radical, which in this case is x minus 1. And then we combine the negative 1 and 1, and that does in fact give us x. Now we compose the other way. We want to find f inverse of f of x. So I want to find f inverse of x cubed plus 1. So in my inverse function, I'm going to replace this x value with x cubed plus 1. So that's going to give me the cube root of x cubed plus 1 minus 1. So if we simplify under the radical, x cubed plus 1 minus 1 is just x cubed. So that will give us the cube root of x cubed, which we know does in fact give us x. So we just verified that these functions are inverses of each other. Now we want to graph them. So we know our original function here, this is one of our transformation of one of our parent shapes. We know the x cubed is one of our library of functions, those parent shapes. And we can see it's with the 1 here, it's been shifted up 1. So we just need 3 ordered pairs on the graph of this function. So if we remember, our key points on an x cubed graph, one of them would be 0, 0. So if I shift 0, 0 up 1, that would give me 0, 1. We know another key point on the parent function x cubed would be 1, 1. So if I shift that up 1, that will give me 1, 2. And we know another key point on a parent x cubed graph would be negative 1, negative 1. So if I shift that up 1, that's going to give me negative 1, 0. So I'll connect using that snake shape, that increasing snake shape that we know. Now the inverse function, our cube root, it's based off another one of our parent functions, the cube root of x, and we can see that this function has been shifted to the right 1 unit. The parent function, the cube root of x, has been shifted right 1 unit. So if we think of key points on a cube root of x graph, 1 would be 0, 0. So if I shift 0, 0 to the right 1 unit, that's going to give me 1, 0. I'll use a different color here. So that will give us 1, 0. Another key point on a cube root of x parent graph would be 1, 1. So if I shift that to the right 1 unit, that would give me 2, 1. And then another key point on a cube root of x parent graph would be negative 1, negative 1. So if I shift that to the right 1, that's going to give me 0, negative 1. And we know that the shape of a x cubed function is going to be that sideways snake shape. Label this point here, 0, negative 1. And then we have the line y equals x. They ask us to sketch that. So we know that's going to be a line going through the origin with a slope of 1. So it's like a diagonal that slices through at 45 degrees through the origin. There's your y equals x. So we can see here the symmetry of the two functions about that line. Also, when we graph this, another way, if you look at the ordered pairs, on our original function x cubed plus 1, we have negative 1, 0. If we switch the negative 1 and the 0, we get 0, negative 1. Here's the corresponding point that's reflected across that y equals x line. And on our x cubed plus 1 graph, we have a 0, 1. If we switch 0 and 1, we get 1, 0. Here's the corresponding point reflected across y equals x. And that third point we graphed on the x cubed plus 1 was 1, 2. Well, if we switch the 1 and the 2, and we get 2, 1. Here's the corresponding point reflected across y equals x. So another way to graph these, if we have the original function graph, we could just switch the x and y values to get these corresponding ordered pairs on our inverse function.